Welcome to Introduction to Manufacturing. Now I'll be covering mechanical properties of materials. So first, what we want to discuss is why mechanical properties are important. Mechanical properties determine a material's behavior when it's subjected to mechanical stresses. And those properties typically include the modulus of the material, the ductility, the hardness, and various measures of strength. And so the dilemma here is mechanical properties are desirable to designer, engineer, such as high strength, but a higher strength makes it more difficult to manufacture. So there is a force fight between designers' the requirements and what manufacturers require. The manufacturing engineer should appreciate the design point of view, and the designer should be aware of the manufacturing point of view. And so that's where the terminology comes that's coined design for manufacturing. What we're trying to do is look at those two viewpoints and merge them into a marriage that works both for the manufacturer and for the designer. So the stress strain relationships are essential to understand because those are the ones that drive the response of the system, the material system. Three types of static stresses to which materials can be subjected to. The first one is tensile, which we can stretch the material when that happens. Compressive, which is a situation where we squeeze the material. And shear, which is a situation where we cause adjacent portions of the material to slide against each other. So a stress strain curve is a basic relationship that describes the mechanical properties for these basic three types. Now, there's many more types, but those are the first three types I'll talk about. And the concept of engineering stress becomes important, and the concept of engineering strain as well. Engineering stress is a force divided by original area, and here you can see the engineering stress denoted as small s and equals force divided by A, where this A that I'm using here is the original area resisting the load. Engineering strain, on the other hand, is the deformation relative to the original length. So what I'm doing is trying to figure out the change in the length, L, the final length minus the initial length, normalized against the initial length. And that's going to give me an engineering strain. The typical engineering stress strain plot looks like this. You take the stress, which is referenced by the original area, always, and they'll have units of PSI, and then strain, which will be non-dimensional. And when I plot it, I have the elastic region up to the yield point, and the yield point is defined as 0.2% offset from this elastic region. And the reason we use a 0.2% offset is a way to normalize the location of the yield strength because otherwise it could be a little bit arbitrary where you select it. And then from there, the stress continues to increase to the maximum load and then fracture occurs. And after the yield point, you'll have a region of plastic deformation or plastic region where any amount of stress above the yield point will cause a permanent deformation to the system. The tensile strength in the stress strain curve should be looked at. So elongation is usually accompanied by uniform reduction in cross-sectional area. And that's consistent with maintaining constant volume. You have a volume material, you're deforming the material, and there's a tendency to maintain constant volume. Finally, the load applied F reaches a maximum value, and the engineering stress at this point is called the tensile strength of the material, this point here, or the ultimate strength of the material. And that's F max divided by the cross-sectional area from the original cross-sectional area before the deformation started to occur. The stress strain curve has interesting behavior. So here's the shape of ductile specimen at various stages. So let's look at what's going on. As I load up the sample, I'm going to start moving through the elastic zone. And then as I continue to load up the sample, then I'll go into the necking region where there'll be a zone where it will reduce, the cross-section area will reduce significantly, and then it will go on to fracture, which is the final stage there. Now, instead of looking at everything relative to the final cross-sectional area, there's some advantages to understand the behavior of the stress strain response, but now not referencing back to the original area, rather to the instantaneous area. So that's where the concept of the true stress and true strain comes into play. The true stress Here is the force divided by the actual instantaneous area rather than A naught, which was engineering stress. I'm using the actual area resisting the load at that particular time. The true strain will be the deformation of the actual instantaneous length. And so the true strain tends to provide a more realistic assessment of the instantaneous deformation per unit length. So here I have the change in length divided by L, but I'm integrating that from L naught to L continuously. This integral gives me logarithmic L divided by L naught. And so this strain now provides a more realistic assessment of that instantaneous deformation per unit length. If I were to plot the true stress versus true strains, things will look slightly different. So here, what I'm plotting here is the engineering stress versus engineering strain in this black curve. But the dashed line corresponds to the situation of the true stress strain curve for the previous engineering stress strain plot that I had shown. And you can see that this dashed line continues in here rather than going down. Why is that? So that necking is occurring, so the cross-section area is decreasing, therefore stress divided by the smaller cross-sectional area means that the true stress will be higher, not lower like shown here. So typically the curves in during stress strain and true stress strain will look similar up to the necking point, and then from there they will deviate where the dashed line becomes a true stress strain curve and the black line corresponds to the engineering stress strain curve. The curve that you obtain from a torsion test curve will be similar as well. Note that the true stress continues to increase continuously in the plastic zone. So in the engineering stress strain curve, the significance of this was completely lost, right? Because the stress was based on the original area, not the current cross-sectional area. That means that in the reality, the metal is becoming higher, stronger as the strain increases, and this property is called strain hardening. So it is important to understand why it becomes stronger in terms of dislocations and grain boundaries. I want you to think about that because there is something going on here that's causing the structure to behave stronger. Now, if I were to apply a log plot to this curve, then you get that this curve here, right? This curve here will become this straight line. And that slope, A over B, can be calculated. That slope here, N, can be calculated. So the region past the necking is where this typically will look like. The start of necking will be here, but it's interesting to see how this becomes a straight line. And so if I were to write that in an equation, because it is a stress, in a log plot, the relationship between true stress and true strain becomes stress equals K, a coefficient which called the strength coefficient, strain to the nth power, where n is a strain hardening coefficient. And the n can be found by taking, again, the true stress strain curve, apply log to that. That'll give me this plot here, and then I can draw a straight line between the data points. That slope is n, and that n becomes exponent here. So you can represent this curve using this equation where n is a strain hardening exponent. We call this a flow curve. It's a major simplification what I'm after, but it goes after what I'm really want to talk about in relationship to the introduction of manufacturing. So there's some categories here that allows us to understand these behaviors. So when n equals 1, in this case, you will have a perfectly elastic material, and that depth, and you can see that here, if n is 1, you get a really linear relationship here, and that's defined completely by the modulus of elasticity. And so this will be typical of brittle materials like ceramics, cast irons, some polymers, and you get fracture rather than yielding. In the second case, N will be equal to some value of 0 at some point. We call this elastic and perfectly plastic. Once the yield value is reached, the material deforms plastically at the same stress level. And the flow curve in this case becomes K equals Y, the strength of the material for yield, and N is 0. So this will happen when metals, when heated to sufficiently high temperatures, let's call that recrystallization temperature, that's how it may behave. The third kind of curve is somewhere in between, right? Which is the curve here that I'm showing, but it's simplified with a bilinear law here. The elastic strain hardening here is shown by here. That's the Hooke's law in the elastic region, so modulus E, and then N could be greater than 0 to represent that curve. Most ductile materials behave this way when cold worked. Now, continuing on here, look at the compression test. If I were to apply a load that squeezes the ends of the cylindrical specimen between the two platens, so I have one here, and I apply a load in compression, you can see that the cross-sectional area has increased like a barrel. So because of that, the engineering stress strain response will be different. Rather than the tension test here at the bottom right, where the stress strain curve for engineering stress strain curve, where the stress is the force is normalized by the original area, and the strain is referenced to the original length. In that case, for tension test, it behaves like this. But for compression loading, the shape of the plastic region will be different from a tensile test because in our case, the cross-sectional area increases. So the calculated value of engineering stress will be higher. So the engineering stress strain curve in a compression test will look more like here in the top right. Now, testing brittle materials. Hard brittle materials possess elasticity but have almost no plasticity. So to find these values, you often need to test by bending test, also called flexure test. The specimen tends to be a rectangular cross-section shown here, and you put two loading supports and apply load here in the center. Bending this rectangular cross-section causes both tensile stress and compression stress in the material, compression at the top, tension at the bottom, and that allows you to then be able to test the flexure strength of these materials for brittle materials. Now, brittle materials do not flex very well. They deform elastically until fracture. So failure really occurs because the tensile strength of the outer fibers here at the bottom are exceeded. And the failure type you will get from these tests is cleavage, which is common with ceramics and metals at low temperature, in which in those cases you get separation rather than slip. So slip is plastic deformation, separation is fracture, which can occur along some certain crystallographic planes. The strength values are derived from the test. You can actually determine that. And the transverse rupture strength is given by TRS equals 1.5 times the force applied, the length between the supports, divided by the width, thickness squared. You can also examine, this is for a 3-point bend test, but there's also a 4-point bend test that could be used. So why stress strain curves are important? Because that's where recrystallization in metals becomes important. Most metals strain harden at room temperature in this manner, right? But if you heat the material sufficiently at high temperatures and you deform it, the straight hardening does not occur anymore. Instead, what you get a benefit here is you get new grains to form that are free of strain. So the metal behaves as a perfectly plastic material n equals 0. So there is a way of getting stress-free new grains to be formed, and that can be done if you heat up the material and you deform it during that time. So this recrystallization temperature is the formation of new strain-free grains, which is called recrystallization. And this recrystallization temperature of a given metal tends to be about 1/2 of its melting point, or 0.5 TM, and is measured on the absolute temperature scale, like Kelvin, for example. Recrystallization takes time. The recrystallization temperature is specified as the temperature at which new grains are formed in about 1 hour. So that's very important for manufacturing. You can exploit this property in manufacturing. If you heat up a metal to that recrystallization temperature prior to deformation, you can allow a greater amount of straining and lower the forces and powers that are required to perform the process. For example, forming temperature metals at temperatures above recrystallization is known as hot working. That allows you to form these materials in a much easier way. Like if I have a tube, I heat it up above that recrystallization temperature, I form it. That's called hot working. And what I'm really doing is I am allowing for new grains to be formed at a free strain behavior, which is highly desirable because the residual stresses may not be there anymore. So with that explains why the stress strain curve is so important. We'll now move to physical properties of materials. Thank you for your attention.